Welcome to The Explainer. Today, we're popping the hood on artificial intelligence. Our mission to completely demystify the honestly staggering costs behind running large language models. We're going to take you all the way from the raw, abstract math that powers these systems straight through the real-world financial realities of actually deploying them. So let's jump right in. To really set the stage for the intense economics we're dealing with here, just think about this number, $12 million. Yeah, training a standard 10 billion parameter model from scratch can cost upwards of $12 million. That is a massive upfront capital expense before the model even generates a single word for a user. The economics at play here are absolutely mind-blowing, and well, that's just the starting line. Okay, let's dive into this. That astronomical price tag inevitably leads us to the fundamental question driving our whole exploration today. Why is generating just a single word so incredibly expensive from a computational standpoint? I mean, what's actually happening inside the machine to cost so much?
To answer that, we need to look at Part 1, the math of self-attention, and the inherent problem with context. Think about how you and I read a book, right? We read linearly. We process it word by word, sentence by sentence, and we just naturally carry the context of the story in our heads. But modern AI, it's built on the transformer architecture, and it doesn't do that at all. It uses something called self-attention. This means every single time it generates a new word, it has to mathematically map the relationship of that new word to every single word it has previously processed in the prompt. It is constantly looking backwards to make sense of what goes forward. This creates a terrifying mathematical reality called quadratic scaling. As the text gets longer, the math doesn't just double, it squares. The computational load grows exponentially with every additional word, making it a completely exhausting task for the system.
Now, before we go any further, we need a way to actually measure all that math. Enter the FLOP, or floating point operation. You can think of this as the fundamental mathematical calculation. It's basically the basic unit of compute used to measure AI processing power. So whenever we talk about the sheer physical effort an AI exerts to give you an answer, we're counting it in flops. It's the core currency of AI computation, and honestly, understanding it is totally key to understanding the final bill.
So, the crucial point is that AI text generation is actually split into two very different phases. First up, there's the pre-fill phase. This is when the AI reads your initial prompt. It processes all those words at once, totally in parallel. Because it's doing everything simultaneously, it's incredibly fast, but heavily demanding on those compute flops we just talked about. It's flexing all of its computational muscle at once. But then comes the decode phase. This is where the AI actually generates its response back to you. And because this happens sequentially, word by word, it drastically slows down. It has to pause, generate, calculate, and this creates a massive memory bottleneck.
Which brings us to Part 2, the KV cache explained, or how we trade compute for memory.
Remember that exhausting quadratic math where the AI has to reevaluate every past word? Well, the KV cache, which stands for key value cache, is a really clever workaround to that exact problem. It essentially acts as a short-term memory bank. Instead of redoing the complex math from scratch every single time it spits out a new word, the AI simply memorizes its previous context calculations and stores them safely right here. By holding on to the keys and values of the previous tokens, the system avoids burning through millions of unnecessary flops, keeping the whole generation process moving.
Now, what's really interesting about this is how system resources actually get distributed to handle all this. While the KV cache brilliantly solves the compute bottleneck by saving on those precious flops, it creates a completely different issue, a massive memory storage problem. Memory capacity gets practically devoured by this caching mechanism as the context length grows. Every word stored takes up physical space on the chip's memory, meaning the more context you feed the AI, the less room it has to actually operate. To put that memory hunger into perspective, if you send a request with an 8,000 token context to a relatively small 8 billion parameter model, it eats up an entire gigabyte of memory just for the KV cache alone. 1 gigabyte, just to remember a few pages of text for a single user. Now imagine running hundreds or thousands of simultaneous users. The memory requirements explode instantly. Now that we understand the internal mechanics, let's look at Part 3, flops translated to dollars and the economics of AI.
Okay, here is a rather painful economic irony for anyone running these models. During that sequential decode phase we talked about, where the AI is generating words one by one and shuffling gigabytes of KV cache data around, Your incredibly expensive $30,000 high-powered GPU is actually sitting idle most of the time. The raw compute speed of the chip is blazingly fast, sure, but the memory data transfer simply can't keep up. It's like paying for a Formula One car that's just stuck in bumper-to-bumper traffic. The processor is literally just sitting there twiddling its thumbs, waiting on data to be moved in and out of memory.
Yet, despite all these crazy hardware inefficiencies and memory bottlenecks, cloud providers have managed to optimize their massive distributed systems to an astonishing degree. They're able to charge shockingly low rates. For instance, you can process 1 million tokens through a model like Llama 3.8b for roughly $0.013. That is just over a single cent. It's a real testament to the sheer scale and software wizardry going on behind the scenes at major server farms.
So, knowing all this, we arrive at part 4, cloud versus the edge, and making the deployment choice.
When a business wants to deploy AI, they essentially face two distinct economic models. On one side, cloud APIs offer a pay-as-you-go structure. You pay per token generated with zero fixed hardware costs. It's incredibly accessible, allowing you to scale up or down without any massive commitments. On the flip side is the edge or local computing. Now, this requires a steep upfront capital expenditure for the hardware, plus your ongoing electricity costs. But the marginal cost of generating an additional token drops effectively to zero. Every prompt you run locally is essentially free once the machine is plugged in.
Let's see how this builds in a real-world scenario. There is an exact crossover point where the economics just flip. If you have low request volume, the cloud is a complete no-brainer. But right around 10,000 requests per month, the script completely flips. At that specific threshold, paying that steep upfront cost for edge computing actually becomes cheaper over time than endlessly renting from the cloud. It represents the crucial breaking point where bringing your AI operations in-house pays for itself. Now, that 10,000 number isn't static, though. For businesses to calculate their exact crossover point, they have to run the math using 3 key variables. First, request volume, which is how often the AI is used by your team or customers. Second, model size, which is the parameter count dictating your hardware needs, because obviously bigger models require beefier GPUs. And third, context length, or how much of that KV cache memory is going to be devoured per request. You change any one of these levers, and your entire economic balance shifts, moving that crossover point up or down. Which leaves us with a really vital question to consider. As open-source models continue to get larger, and as your own business usage inevitably scales up, are you endlessly paying rent for compute you could, and economically should, be owning? It's a critical calculation that will absolutely define the next era of AI deployment. Thank you so much for joining me for this explainer, and I highly encourage you to apply these economic principles to your own tech stack.